Okay? So when we attack here, is this an SN1 or an SN2? Good. SN2. So we're going to attack here. Leaving group leaves. So get that the same. Okay, so does this satisfy my Walden inversion of configuration? Yeah, it does, because I switched any two. If you switch any two substituents, that switches it from like R to S, right? So that'll give you the enantiomer if you switch any two substituents. So when I attacked from the backside, I forced fluorine down here and added up here. Does that make sense? So it doesn't have to be strictly the dashes and wedges, okay? All right, so this does satisfy my Walden inversion of configuration. Let's get the absolute configurations on these. So this is number 1 right here. That's number 2. That's number 3. And that's 4. So if we go like this, 4 is already to the back. So this is S. Fair? Here we have number 1, number 2, number 3, number 4. That's S. Is this a Walden inversion of configuration? Do we still convert or invert it? Why? Bromine is heavier than fluorine. Yep. So that's fair. That's fair. So S, fluorine is heavier than oxygen. So these are both the correct configurations. Did we still do our Walden inversion of configuration? Earlier, a second ago, we just said that we had. Did we not? The priorities changed. In this one, bromine had a higher priority over fluorine, right? Well, now fluorine has the highest priority, and what replaced the bromine is the lower priority. Just because it's S and S doesn't mean we didn't do our inversion configuration, right? So there are scenarios. And again, this is what separates good students from great students right here, okay? We made the mirror image, right? However, what we replaced the bromine with is lower priority. So when we redid our configuration, it just happened to be S still. A Walden inversion of configuration doesn't guarantee switching from an S to an R. It guarantees that you switch the orientation of these things. S and R is dependent on the priorities still, right? If the priorities change, S and R might change. All right, so I just want to show you guys that is a possibility. All right, questions? Okay. All right, so I'm going to blow through this shit. What's that? Okay, yeah, just shout at me. Okay, so electrophilic addition reactions, all right? Again, you're going to be predicting products. You should know the mechanism. You should know that most of these are going to have a carbocation intermediate. So they're subject to rearrangements or whatever. But you will need to be able to see the products, okay? So here, All right, so here's our product right here. So this is Markovnikov addition. I don't think there's anything else special about that one. Okay, so this one right here. Our intermediate looks like this. So we get a bromonium ion. Yes? Sorry? No, it's just what carbon are you adding it to, right? It doesn't matter here. This isn't a chiral carbon anyway, so you don't have to show stereochemistry on one of these. It's just which carbon did the chlorine add to, the most substituted or the least substituted. Well, we went through a carbocation. The electrophile always adds to the least substituted carbon. Your nucleophile then attacks this electrophilic carbon, which is just the carbocation, okay? Yeah, so we care about where it added in this case. There's no sin or anti on this one because this is planar. This is sp2 hybridized, this is planar, right? So we could add with equal probability to the front or the back. Here, this is a different story though. So this looks like this. We don't have any other nucleophiles in solution except for the bromide. This solvent is apolar, non-nucleophilic. So our bromide is going to attack. This carbon is more partial positive than this one is. So this will attack here. And it can't attack from the backside because we got this big old bromine sitting here, so it attacks from the front. So you're going to get so this is anti-addition. Okay, so this is adding water. Our transition state on this one looks like this. In this case, the boron is the electrophile. The electrophile always adds to the least substituted carbon. Boron is the electrophile in this case, not the hydrogen. And so when you replace it then with oxygen, it's on the least substituted. Well, that makes this anti-Markovnikov. And H and OH minus added to the same side, right? Bless you. So this is also sin addition. These are important. If you know it's anti-Markovnikov and you know it's sin addition, you don't got to draw the transition state. You don't have to, because you can just say, oh, boom, anti-Markovnikov. The H adds to the most substituted. So I'll put the H there. OH minus must add to the least substituted. I'll put it there. Oh, it's sin addition. I'll put them on the same side. Call it a day, right? If you know these little facts about each reaction, then you don't need the mechanism. You can just draw the product. And that's where you want to be for this ACS. Boom. Oh, I know this. I know that cleaves. This thing tells me that it's a free radical mechanism. MCPBA, that's an epoxide right there, right? You want to know that stuff off the top of your head without thinking about it, okay? let's do the next one. So this is oxidative cleavage. Ozonolysis results in ketones and aldehydes. This is not as strong as potassium permanganate as an oxidizing agent. So it stops short of a carboxylic acid. All right? So here, the easiest way to do these, break that in half. Okay? So I'm going to get this. And I'm going to get boom. Break it in half, separate them. So this is an aldehyde, and that is a ketone. And that's just a result of what I drew. That's all. If this little guy right here didn't exist, you get two aldehydes. So just break that thing in half, slap O's on them, call it a day. This is a free radical mechanism. So we're going to get no, okay, so this is anti-Markovnikov. My bad, hold on. And I drew that wrong anyway. So this one results in an anti-Markovnikov addition. And so we're going to be here with our bromine. And then our H adds here. If you have I don't think I put it up. This peroxide, so if you have a peroxide bond that's just a very weak bond, and it breaks homolytically, resulting in a free radical. So this peroxide, when reacting with this, will result in a free radical mechanism rather than the ionic addition that you have over here. So this peroxide only results in an anti-Markovnikov product if you're working with HBr. If you're working with HCl or HI, it doesn't affect them. It only affects HBr, okay? So again, that's like another little fun fact. If you see HCl and HOOH, looks just like this. Still Markovnikov addition. But if it's with HBr, you're going to result in that free radical mechanism, okay? So there's an exception. This is like just a one little caveat, one little exception here. All right, MCPBA. This is a peroxybenzoic acid. Peroxybenzoic acid. What matters is it's a peroxy acid or a per acid, which means it has one of these groups on it. R, C, O, 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 H. Peroxide bond. Again, this is a very weak bond. From MCPBA, you get Should have just done this. Epoxides. The reason they use MCPBA is because in acidic conditions, this is a very sterically strained ring structure, right? Typically, sp3 hybridized bonds are 109.5 degrees. But this forced triangle, that's like 60. That's tiny, right? So there's a lot of ring strain in there, and it wants to just break apart. So it doesn't take much. This is already an ether. Ethers are sensitive to acids. Again, that's another thing you learned in lab, right? When you're doing your extractions. So this ether is very sensitive to acids. So if the conditions are too acidic, it'll open up. So when you're using MCPBA, the resulting conditions within the solution are not acidic enough to continue opening up the epoxide. So your final result with MCPBA is an epoxide. All right, this is osmium tetroxide. This gives you, well, I'll draw the transition state here first. Oops. So this is what the transition state looks like. And just like when our NABH or our BH2 added to the same side like this, we got a syn addition. Same thing. We're going to get a syn addition here as well. All right, this transition state looks the same as that. So it's another, oh, good. Yeah, go ahead. Good, okay. All right, so this, again, this transition state looks exactly the same, just put Mn in there instead of the osmium, right? And so we're going to get another, this is a glycol. And maybe I should draw the right shape. That's what I get for switching it up. So here, again, this is syn addition. Okay, so here we add 2 hydroxides, syn addition. Here we add 2 hydroxides, also syn addition. This, 1, 2, 3, this is a peroxy acid. It has the same functional group as this metachloroperoxybenzoic acid. This is just like a methyl peroxy acid or something. What do they call it? Like formic or something. Doesn't really matter. Anyway, so first, we're going to get an epoxide. First. The problem is the conditions in solution are too acidic for this thing to be stable. So under acidic conditions, it's going to break apart. So basically, this O grabs this H, makes it a good leaving group, and then water attacks the most substituted carbon and this one leaves. Well, it can't attack from the backside because you got this whole giant thing back here. So it has to attack from the front, pushing this methyl group to the back. Exactly like this. There are similarities between these, right? If you add at the same time to the back, you're going to get syn addition. If you get one of these ring structures and then something else attacks, you're going to get anti-addition. This and this look very similar. And the mechanism is the same, right? So there's a lot of memorization, but there are patterns within here that you can recognize that mean you don't have to memorize as much, okay? So this is going to result in the methyl group being pushed to the back. We'll get an OH here. And then this one has no reason to switch its position or anything, so it's still to the back. So here are 3 different ways to get a glycol. 2 of them are syn addition. 1 of them is anti-addition. So this is acid catalyzed opening of an epoxide is what this is called. You have an epoxide, acidic solution opens it up, you get a glycol. A glycol is a vicinal diol. Questions? Okay. Oh, we already did this one. Okay, so we had potassium permanganate cold dilute. Now we have potassium permanganate warm and concentrated. Well, when you increase the temperature, increase the kinetic energy, this is an oxidizing agent, right? On the last one, it made a diol. So we added hydroxide groups or alcohols to our hydrocarbon. This is now strong enough under these conditions to break apart this bond completely. So this is oxidative cleavage, all right? Now we had another one, so I just want to compare these two then. So oxidative cleavage, break your double bond and then draw it. So here, so we got this, but this is a much stronger oxidizing agent than the ozonolysis and the ozone. So this is going to result in ketones and carboxylic acids. And it'll result in CO2 on a terminal alkene. So this would be an aldehyde, but it gets further oxidized because potassium permanganate is such a strong oxidant that we end up with, well, that was really poorly drawn, this guy right here, okay? Now again, this is ozonolysis. Here we get ketones and aldehydes. So again, we're breaking this, and we can draw the same thing. Well, that remains an aldehyde, and then there's your ketone right there. This is a reduction. Adding hydrogens is the opposite, has the opposite effect. This is a reducing it, okay? So here, our product is going to be right here. What kind of addition is this? Syn addition. Good. This is a syn addition reaction. This is platinum or nickel or palladium catalyzed addition of hydrogen, right? It's just a reduction reaction. The catalyst has basically attacks from the same side in this case, okay? So similar, okay, they're on the other board, but similar concept. So this is a syn addition. All right. This is acid catalyzed addition of water. So this is going to be Markovnikov and subject to rearrangements. Because our intermediate is a carbocation, okay? So here, we'll get this guy because this is tertiary, this is secondary. H adds to the least substituted, OH adds to the most, so this will be either forward or backward. Here, we're going to get our carbocation, but again, if it's subject to rearrangements, it's going to come down, so we're going to get this instead, and then when the water adds, it'll add right there. So here instead of on this spot, right? So we'll get a rearranged product. This is special about this addition of water versus the other additions of water. There are three ways to add water in an electrophilic addition to an alkene. This is one of them. This one gives you Markovnikov and rearrangements. This one, oxymercuration, demercuration, gives you a Markovnikov and no rearrangements. And it's anti-addition. So this is, there's no rearrangements because we don't form a carbocation. We form a mercurinium ion. And it looks eerily similar to an epoxide or a bromonium ion, right? And so our reactive intermediate looks, it's going to be like this. Like this, okay? Well, water attacks the most substituted carbon, and then it's later reduced by NaBH4. So you replace this mercury with a hydrogen. So you end up with we'll just say OH. Anti-addition, Markovnikov. Here's the other one. This is anti-Markovnikov. And syn addition. So this gets us if you know it's anti-Markovnikov and you know it's syn addition, slap them on, call it a day, right? That's why it's so important to know this stuff. There's memorization and there's understanding, all right? You need both of them to successfully take this test. This is very similar to this one right here. The only difference is our solvent. So with that one, when you form your bromonium ion, The only nucleophile to attack that electrophilic carbon is a bromide ion that you just broke off. But here we have a bunch of water. Water is way more abundant. This is our solvent, so this water is way more abundant. So it's more likely that you're going to have the water attack that electrophilic carbon than a chloride ion floating around in there, right? So we're still going to be anti-addition. We need to know that water attacks the most substituted carbon. So whatever we started with, anti-addition, water attacks the most substituted, which is that tertiary one. Okay? Questions? All right, so I know we just blew through that. You guys okay sticking around for a little bit longer? Okay. This can be cis or trans, doesn't matter. The chlorine is going to add to the most substituted carbon both times because it's Markovnikov. So both of these both bonds, it's going to add to the most substituted. This is going to break it all the way down to an alkane. And I should say it reduces it all the way down to an alkane, which is exactly what it does. So here you're going to get this. Done. And remember, this is syn addition, but who cares because they're all just hydrogens. You only got one on there anyway. This is going to stop it at an alkene. This is called Lindlar's catalyst. And I believe this one is syn. Let me double check. Addition. Syn addition. So that's another important point you need to know. This is syn addition. This one is anti. And I believe I forgot. Okay. So here, this one is going to be still stops at an alkane. Sorry, alkene, but it is anti-addition. So here, you're going to get your anti. Here, So similar to this here, but there's no more carbon-to-cob, anti-more carbon-to-cob because you're only adding bromines. So you're just maxing it out there. This is going to give you a diketone. Let me double check on that. There we go. And not surprisingly, if it's terminal, you'll get a carboxylic acid out of it. If you have internal alkynes, you'll get a diketone. If you have a terminal alkyne, you'll get a ketone on the one that's secondary, and on your primary, you'll get a carboxylic acid. This again results in cleavage. 1, 2, 3. So here you're going to get carboxylic acid, and because this is terminal, we'll get CO2. On an internal alkyne, products are 2 carboxylic acids, because you're going to have other carbons to attach to that. This you may have seen when you were working with like acetylene and the synthesis stuff. So we have an H right here. Na, we know that means nothing. And this NH2 minus, this is a strong enough base to abstract this hydrogen. So this results in a carbanion ion. And then, you know, our spectator sodium is just nearby. And then we'll get, you know, NH3. But we don't really care about that. We care about this. This is what you get, a carbanion ion here. This results in, this is Markovnikov. This is very similar. Oxymercuration, demercuration. It's Markovnikov. It's Markovnikov there. It's the same here. We just have to use a little harsher chemicals because this bond is a little stronger. And what we get here, 1, 2, 3, 4, 5, is a ketone. This is Markovnikov. And this is anti-Markovnikov. And so you'll end up with an aldehyde. So that was really fast. Yep. Questions?
Will you take the test for me?
No. Yeah, I don't know. I'm attached to it. I'll tell you what, if you can pull that off. All of the stuff that I was using to like pull problems and stuff, it's on that Canvas page. I put them up there today. It's all my crappy handwriting, so enjoy. But it's all up there with the answers, so you have that available to you.
Thank you.
Yeah, no worries. Obviously, let us know if you have questions. If you didn't get one of these,